one thing that I think science can benefit a lot from art, it's because science has a very high entry threshold. It feels very hard for someone that has not had science education to get into science and to start to understand it and to start to trust, so that when the scientist communicates something like the Earth is getting warmer mostly because we humans are producing CO2, if someone doesn't have access to science, you don't really trust that person. But art has a very low entry threshold. It doesn't mean that there is no entry threshold. You have, and the more you study, the more you learn, the more you see. But a kid can appreciate something from art without having seen anything of this artist from before. And that's much harder with science. And then we can use this kind of like a low entry threshold as an open door for science communication. So art is an open door for science communication. My name is Marcel, and I work at PoreLab together with Alex. So that's the Porous Media Laboratory, and it's a center of excellence in Norway. And I'll be talking about experiments on the motion of liquids and gases through porous materials. And I'm going to try to explain what this all is. And this is not really a science talk. I talk to scientists all the time. That's like Monday to Friday, so today's a bit different. But basically, just to have an idea of what we do, this is the mission of the center, the center's mission. It's to unify and advance the understanding of porous materials, of porous media. And this here is a little model that you could think of it as kind of like a model of an aquifer, of like an underground aquifer. You know, like most of the water we consume comes from aquifers, and then the aquifer is a porous medium. The soil is a porous medium. Rocks are porous, our clothes are porous. Pretty much everything you see is like, it's more likely that it's porous than it's not. And the water is in the aquifer, and we want to understand how it moves. We want to understand how to be able to make use of it, right? But so this is very connected to hydrology, to engineering, and we are kind of like more on the physics side. So we try to understand the basic process in itself, like how does a liquid or a gas moves inside something porous. If it's not porous, it's a lot easier. It can go like a straight line. But if there is like lots of tortuous paths inside, so what does it do? And this is a picture from when the center was founded. I think it was 2017. I'm not going to go into details on anything, but the idea is a lot of the things that we do are very visual. And this is, to me, it's very interesting. It's nice when things are visual, because then you can start to get a bit of a connection to it, and you can start to have an intuitive understanding of things. And this is very nice. And so we've been collecting experiments and simulations. So scientists and physicists, or scientists in general, kind of like come in three flavors, depending on how you define. There's people like me doing experiments. There's people like Alex doing theory, and there's people doing simulations. Alex does a bit of both, but there's kind of like these three types of things. Simulation, so that's people using the computers to try to mimic nature, to understand nature better. The experiments, trying to probe nature to see how it behaves, and the theory, trying to put order in the house. So we have all of that at PoreLab, and a lot of the either experiments or simulations, they are just very interesting to look at, even if you don't know what it's all about. So we had this collection, this exhibition, that we just gathered interesting images to show to the public. This is one of them. I'm not going to go into details of what these things are. I can explain to you after, but that's not really the point here. The point is really just the aesthetics of it, right? So this is one of them. This is an experiment that we put the colors on the computer, but it's the result of an experiment. Here's another experiment, has to do with the carbon capture, how to get CO2 from the atmosphere and store it. This is another experiment, has to do with dissolution of gypsum. If you break your arm, you put like a gypsum around. This is water dissolving it somehow. And these things are beautiful. And we've put up this, we've printed these pictures, and we managed to get permission to exhibit them in Oslo, in Norway, right next to the city hall. But we also made it so this is the physical exhibition, but we also had like an online exhibition. And this is something that I guess artists are probably very used to, this kind of platform. It's called Kunstmatrix. But the scientists do not. I mean, like, no one in the sciences knows about these things. So like when we show this, they're really amazed because, okay, this looks like a museum. We can walk around, you can see the things on the wall. And this is on the website. So if you go at porelab.no, you can find that. And I think that we have spent a lot of money, trying to design all of this. There's a bench there, there's all of these things, and it's very easy to do on the website. But you can go, you can see the pictures there, and if you click on any of them, you have a little bit of information of what the science is. But again, the focus of this was not really on the basic science behind everything. It's just that these things are interesting to look at, and that can be used to trigger curiosity in itself, right? To trigger, you look at something, you find it beautiful, you want to know more about it. So, and I think that's also like what Mirella saw first, probably the exhibition online, and then she contacted us back in 2021 or 20? Oof, it's been a while. Yeah, and we are very grateful for that because this has been really like a very, very nice opportunity for all of us.
We are the same.
Yeah. So, porous media flows are everywhere. When we talk about flow, that means a fluid moving. When you talk about fluid, that's either a liquid or a gas. Scientists tend to overcomplicate things sometimes that are not necessary, but water or air moving inside something porous, this is a porous media flow. So here you see like someone painting on a little canvas, something like this. It's important to know the porous structure of this type of things, because if the screen, like the canvas was not porous at all, maybe the ink would not permeate it, it would just like flow down. If it is way too porous, maybe it will just go through and like go to the other side. Like people that are into calligraphy, they care a lot about the structure of the paper because you don't want what they call feathering. You don't want like the ink to like go like on the side of the letter. That's kind of not beautiful. So this is an example. If I speak too fast, just do something so that I cool down because I tend to rush. So when water rains down, it permeates the soil. That's also an example of porous media flow. And the water gets trapped under the soil, and that's super important because the roots of the plants, they need to have access to this water. If the water just went through all the way to the bottom, like the center of the earth or like some solid rock, the life would not exist. I'm very much into coffee, and any process where you are making coffee is an experiment. It's an example of a porous media flow. Here is like the usual percolation we do at home. We pour water onto the coffee grounds. The coffee grounds is an example of a porous medium. And then the water goes through and gets the flavor out of the coffee, and we drink it. But you see, all of this porous media here, this natural porous media, they are very nice, but they are not transparent. So we cannot see inside. And physicists, the way that we work is that we take something from a reality, we try to simplify until we can make some sense out of it. And then we try to add some complication from that level on. But it's important to reduce so that you get to a point where you can understand. And that's kind of like the principle here. We reduce this type of system into something that we can see inside and try to make sense out of it. So this is a porous medium, like a soil, like a rock, but it's transparent. It's made out of tiny glass spheres like this. And the blue is water and the white is air. So you can think of this as a column of a soil, for instance. It has rained the day before, so the water has filled up all the voids, the pores, the space between the soil grains. And then it starts to evaporate. And then you see like here is air coming from the top. So this is, you can think of this as being like just a soil evaporating. And then you see that there is lots of bits of water that remain there. This is very important because this is the water that plants have access to. It's water that is trapped in the soil. Even if the soil looks dry, there's water under. And the plants have access to that, so that is important. And all right, so I was thinking of bringing something like this here, but that is kind of boring and big, and then I didn't know what to do. And I also didn't know so well how to talk to artists because I talk to scientists all the time, and it's very easy to talk to scientists because we're kind of like every scientist is almost like the same scientist in a way. We kind of like follow the same routine. If you're giving like a talk to scientists, if you put like an introduction, development, a conclusion, and then you make some connection with things that other scientists have done, the references and such, so we like that, and then that's basically it. But I don't know what art is like, so I was thinking of like doing a little bit of hypnosis to you to see if I could like win your confidence and make you like my presentation through that. But that was also like not really working, because as I was making the presentation, I was looking at this and it's extremely effective. Actually, I was getting like hypnotized myself. So I decided to move to something else. So this is an experiment, and it's also an artwork that I brought here to this exhibition, and I want to show that to you. I call that Porous Hypnosis 1 because I had to give a title to the art. And it's 1 because it's the first one, maybe of a whole series. It's the only one that exists so far, but maybe there will be more. And I think I'm breaking the rules here by actually showing a little bit the thing. Yeah, before the opening, but I have another one there, and you're not seeing the whole thing. You're just seeing parts of it, because what's important is to interact with it. So this is Porous Hypnosis 1. Move it around, please. It's impossible to break, so you don't have to be too careful. It's artist proof. I have tested it with like many different things. But okay, so here we go. There is a liquid there. I'm injecting air. And air goes around and around and around, making you dizzy a little bit like that. And I think that's just like nice to look at. I mean, you could look at this for very long. I've been looking at it for very many years. Maybe too many years, who knows? But it is an interesting thing to look at. But even more interesting is, so here you see like this is air coming in, okay? Air comes in, air is white, blue is liquid, water. More interesting is if you inject both air and water and air and water and air and water, because then you start to have this big race, lots of dynamics, lots going on, bubbles that go past very fast, and sometimes you have like big bubbles that break up in smaller ones, and sometimes you have small ones that merge and make big ones, and it's a big race like this. And I think it's very interesting to look at. It's nice to follow some of them around to see how the shape changes. And you can do lots of things. You can do the opposites too. You can like remove from here, and then the spiral goes the other way around. You see, like from the center to the extremes. And if you do it very fast, then suddenly you have like lots of tiny bubbles. So this is all interesting to study. And it is an active area of research, how these things change if we do it fast or slow. Not really on a spiral, because this is, I think this is much nicer. We should do it on spirals, but for science, like for physics, we typically go either circle or square. It's basically the two shapes that the physicists have learned from the scientists. But this is the spiral one. And if you look at it close enough, everything is interesting if you look at it close enough. So this is the same droplets, but there is just so much going on if you look with a big macro lens, a big camera. Sometimes you see like a tiny little droplets like this that tends to stay stuck forever until a bigger one comes and pushes it around. Sometimes you see like the droplets kind of like flickering a little bit. It's almost like it's feeling that there's another one coming. And it really is like it's almost like it's hearing that there is another one. And it really is almost like hearing, because when we hear, this is sound waves, and sound waves is like pressure waves in the air. That's how you hear me. And this droplet there, you see it's kind of like fluctuating like this because it's feeling a pressure wave from something that happened far away. So it's kind of like hearing the other drops. And this is how the thing looks in the lab. And I cannot show it because Mirella is looking mad at me because this is supposed to be a surprise, so I just skip it. Yeah, you get the chance to play with this if you come on Friday or any other day until the end of the year, I guess, while this is around. But there is an experiment that you can do at home. It's a tea bag experiment. That is something that simulates this, and it's very easy. You just get a tea bag, you put it's wet, you put it on a napkin, and then you see what happens. And two things are going to happen. The tea water is going to get sucked by the napkin here, so the napkin gets wet, and air starts to enter from the surrounding into the tea. And there is an interesting thing here, that the water going on the napkin is kind of like a continuous process. The napkin starts to get wet and wet and wet and wet, more or less continuously. But the air going into the tea, it's an intermittent process. It goes in big jumps. It does nothing, and then it goes a big, and I can show you here because I did the experiment and I filmed it. So here comes the tea bag, and then here I move the camera, and then you see like these big pockets of air. They are very intermittent on the way that they enter the porous medium, the tea leaves here. And this is basically the same thing that you'll be seeing on this experiment there, just that I didn't have tea, I had a 3D printer, and then that's how it happened. But now we will take a little break from porous matter. You've had a lot. So yeah, take a little break, we'll talk about birds. Okay? This is a bird. Figure 1, a bird. Figure 2, has anyone seen this kind of thing before? Yeah, some. So this is called a murmuration, and it's a very interesting thing. And if you turn on the birds like that, they do all sorts of strange things. And it almost looks as if this whole thing is an organism in itself. Almost as if it had like an intelligence of its own. As if it was. So what's happening here is that there is a predator. I don't know if you can see, but there it comes. Whoops. There. So it's trying to catch the birds. And then the whole thing kind of opens in a hole like this to avoid the predator. And it's an emergent phenomenon. It's a collective behavior, which is very strange because you know, like how can like the birds have like a kind of like a collective intelligence to like move? Each one knows which way to move to avoid the predator. And the funny thing is the predator is typically faster than each single bird. So if it is like a one-to-one, the predator would go and catch the bird. But here the predator is following one bird, but then suddenly it's another bird because all birds look the same. And the one that he was following is moving that way, but the next one that's kind of there is now moving this way, and it gets confused and never catch them. And this is a painting I like a lot, Van Gogh, Wheat Fields with Crows. And this is maybe how it happened in real life. I don't know if it is, it's just found it on the internet, but maybe it was. And this is, I could talk about this forever. You know, there's nothing, I don't work with any of this, but I just think it's very interesting. Look at the size of this. This is scary. Look at the size of this building. Like, it is a huge thing. If this decides to attack you, no, there's no way out. And you can see waves of information going through that thing. And it's a very interesting example of collective behavior. And it's here to show a little point that I think it's very important. And that is in some systems, in fact in many systems in nature, the fact that you know a lot about one little entity of the system does not mean that you know what happens when you put a bunch of them together. Because something that we call complexity shows up, complexity arises. And this is an important idea in physics and I think also in society and in art perhaps. And it's the idea that this here, constructivism, going from like a small unit to a larger whole is not an easy path. And this was expressed very well by this guy here, Philip Anderson. He won a Nobel Prize. And this is the sentence that he had to describe this. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. And this is, I think it's a very important concept. It's a concept that I think it should be hammered down on the head of every science student and possibly of every person in life because it's very, very important. And it's a part of a philosophical debate between these two kind of like currents of thoughts here, reductionism and constructivism. And this is on this paper here that's called More is Different, which I think is a brilliant title. I'm going to go briefly through some of the ideas here. I'm not going to go deep into the paper, but you can find it very easily on the internet. So reduction is this idea here that everything can be explained in terms of simpler, smaller quantities, okay? So if you start, for instance, with an organ, a human organ, that's made out of tissues, that are made out of cells, that are made out of organelles, that are made out of molecules, that goes all the way down to the atoms. And then, if this is true, and we strongly believe this to be true, it's very easy to be led to think that this is all that is fundamentally important and that only this type of person matters. The scientist that is working on the very fundamental laws of the universe, on the structure of matter, how atoms interact, and then this is the only one that should be paid because all the rest follows from that. And the point from this paper here is to oppose to this view, okay? And I'm not going to go through it, but he had like this little table here. It's a table of the sciences, And the idea is that the science X obeys the laws of science Y. Okay? So social sciences, it's made out of humans, people, obeys the laws of psychology, which obeys the laws of physiology, which obeys the laws and then you get to biology that obeys the laws of chemistry and that obeys the laws of elementary particle physics, which is basically what atoms do. This is true, but this hierarchy does not imply that science X is just applied science Y. There is important fundamental research that can be done in all these levels here. So again, if you know everything about one entity, it doesn't mean that you know what happens when you have a bunch of them important, because even though reductionism is a very important thing, it does not imply constructivism. And I think if we can do a little bit of a stretch here, I think we can say the same to be true about art and science. So humans are made out of atoms, and creativity and ingenuity is something that comes out of human, and art and science comes out of creativity and ingenuity. But there is no way that science will go from the atoms to art. Physics or science in general is not going to solve art. And I think that's kind of like in line with the things that we heard before from Michaela and Alex, and that we need both. They are complementary, and it goes either one or the other, but they go together in a complementary way, and I think that humanity benefits a lot from that. Okay, so complexity, more is different also in porous media flows. So we have this beautiful thing here that we like a lot. It's the result of an experiment. I'm going to show this experiment after, but we like it so much that it made it to the logo of the group. And when I joined this group long ago, first thing I did was to try to learn what complexity is, because everyone around me was talking about this thing. And what you do, you go to Wikipedia when you don't know something, and then I tried to find the definition. And then I found this right on the beginning of Wikipedia. The only consensus among researchers is that there is no agreement about the specific definition of complexity. And if you are like a relatively young student starting your career, this is very disappointing. If like the people that have been studying this forever don't know what the thing is, the basic definition, then what do we do? But there are examples. So this is kind of like thought through examples. And complexity is generally used to characterize something with many parts, where these parts interact with each other in multiple ways. Okay? And it's nice to go to the roots of the word. So complexity, it's a com, which is together in Latin, and plex, and it's woven, so it means woven together. And that is actually different from complicated. The roots plic is folded. So complexity means woven together. And one idea that comes very frequently is this idea of collective behavior and pattern formation. Okay, so everyone that has been to Timisoara can not miss this. You have all seen it. I have seen it. It's your beautiful cathedral that you have somewhere there, I think. Maybe there. No, there. Yeah, there. Yeah. And it's a beautiful thing, and it's almost like a monument to patterns. There are just so many patterns there. We see the stripes on the towers. We see like this beautiful tiling, different types of tiling, and like this hexagonal structure here, very interesting. Very many different types of patterns. And then when we look at these patterns, we always think that for the pattern to exist, there must be a patterner. I don't know if this word exists, but if it doesn't, I'm inventing it now and you understand it. It's the person that made the pattern, okay? But in reality, nature itself is very great at making patterns. And these are snowflakes. And I was telling yesterday, Benji, I don't know if he's in the room, but these are very, very early photographs of snowflakes that were taken by this guy here, Wilson Bentley. He was known in his community as Snowflake Bentley because that is the one thing that he did it, and he did it well. This is 1902. He used that camera and he took these kind of pictures. He wanted to make a catalog of all the snowflakes. So you see this one is a snowflake 893, this was one 897. They are all different. They all share this kind of like a six-fold symmetry, but they're all different. And I am really impressed by the quality of this because I have access to some very nice cameras in the lab in Oslo, and if you gave me a snowflake and asked me to take a picture of it, I would never do half as well as this person did in 1902. So here are some ripples in the sand, and it's not very hard for you to see that that kind of looks a little bit like this. the stripes on the zebra. How did the zebra get its stripe and its stripes? And one person that did a lot to try to understand pattern formation in nature was this guy here, Alan Turing. He's one of my scientific heroes. He's the father of computers, basically. And there's a great movie about him, Imitation Game. And he had this paper, The Chemical Basis of Morphogenesis. So this is basically, so this is a hardcore mathematician, as hardcore as it gets, basically. He made some set of rules that could be a chemical reaction, and so it could be something that a biological system could do. And that if we follow these rules and you repeat and repeat and repeat, you can get lots of different patterns. So this is one hypothesis of how the zebra got its stripes and how every kind of pattern that we see could be formed. And he was a bit of a funny type too, so he said this: well, the stripes are easy, but what about the horse part? So the horse part, he didn't really explain, he left that to the biologists. So again, back to this experiment. I said that this is the result of an experiment, and to me it's really amazing like how this is not made either by a biological thing like a coral, like an animal or something, or painted by a person that willingly make this drawing. This is really water and sand. So what we do, or what the people that did this did, is just to get two plates. You put one parallel to the other. There's about 0.4 millimeter distance here. And then you put some water and some sand inside, like this. So if you look from under, camera is here. This is it. Golden part is water and sand. And then you start to remove the water from here just with a syringe. You do it very slowly. And this is what happens. So here is a video of how this pattern shows up naturally. It's air coming from the sides, pushing the sand away, that somehow makes this. And to be honest, I don't really understand it. It's really hard to say that you understand this. You can make like simulations with like some rules that kind of like mimic the process, but really to say that you have like an intuitive reasoning, how could this come to be? It's hard. And what you are left with is just the dry sand. And this is another instance where you can think it doesn't matter how much you understand about one grain of sand, or like how two of them interact with each other. How can you predict this? Complexity arises when things scale up, when you have many, many grains of sand. So this is interesting. Now I'm going to show another experiment, and now it's something that is 3D printed, and you see that this one here is a very ordered system because there is a hexagonal structure there. So the pores are kind of like positioned in a very ordered way. And then if you inject air in the center, so air enters, black is water, it makes kind of like a snowflake. It kind of like follows this very beautiful hexagonal structure, which is a kind of like a reflex of the order underneath. So the pattern, what you see, the air, the snowflakes, it kind of like reflects the underlying structure of the material that was made in a periodic way like that, in a crystalline way. So by periodic or crystalline, I just want to say ordered, that these pillars are kind of like, that is not organized, but it's kind of like a random. So these little dots here, they are glass spheres and they are randomly positioned now. Okay, so you see you don't have like that structure from before. And then you also get an interesting pattern, but now it doesn't have like this kind of like hexagonal structure anymore. It has some randomness to it. It's still spreads, but in a kind of like a random way. And so this is what we call the fractal, and we have studied it quite a lot. And depending on how fast or how slow you do this process, you get different types of structures. So this is just water, air going inside this material. This is the same thing, just that one is slow, this one, no, this one is fast, this one is slow. And you see like this one here is kind of like a fatter, like the fingers are a bit wider. And we try to understand these things, why just changing the speed made a difference from one to the other. One thing that I spend a lot of time on is to digitize this image, is to put it on the computer in a way that makes sense. So this is just the same experiment, but the color here means the time that the air has arrived at a little point. It's just the same thing made with color so that it gets nicer for us to understand and study. And then we get very many different types of patterns, and we try to understand how these patterns differ if you change the experiment. So if you do the experiment slow, you get something like this. If you do it fast, you get something like this. If the porous medium itself can deform, you get something like that. If it cannot deform, you get something like that. So you get a lot of different structures depending on how you make the experiment. Okay, so here's one important thing that I'm trying to repeat this point, that going from a small scale to a large scale is very hard. If you understand everything about a little bubble, it doesn't mean you understand what happens when you have lots of them together. And this is important. This is not just fun for scientists. It's very important because the scale we interact with porous materials is typically very large. We don't go at nature at one pore. We go to an aquifer that is thousands of kilometers. So there's many pores. It's very large. And then we have to be able to translate the science that we understand there to the sizes, the scale that we interact with the systems. And this is the job of a lot of people, us in PoreLab also. And it's very important. You see, like this blue here, this is called the 𝐴𝐚𝐫𝐬 aquifer. It's one of the biggest reservoirs of drinking water in the world. Depending on like how you count how the population will grow, this is either enough for, it's enough for something between 200 to 1,600 years of the whole world's consumption of drinking water. It's a lot of water, and we need to understand these things. So, Michaela said about experiments and the price of experiments and some experiments that you could do at the kitchen. So here's one that you can do at the kitchen. I'm going to show you. I'm going to show you how to poke a hole through water, and you can do it at home. And everything you need is some cinnamon. You put some cinnamon on the top of water, just like a sprinkle, a little bit like this. This is a glass of water. And then you try to poke a hole with a fork. And that's what I do there in my kitchen. And it doesn't work, because I'm trying to poke a hole in water, and that's kind of silly. It doesn't work. But then if I use the other side of the fork, somehow it works. And the question is, why? And it's not just one experiment. You can repeat it, and it works every time. Does anyone have a clue of like what's going on there? What's different with like that side of the fork? The answer is soap. You put a tiny, tiny little drop of soap in one side of the fork. And soap is something that breaks through something called the surface tension. Every time we see water, air here, there is kind of like an interface between these that is almost like a physical membrane. It's almost like a balloon. And some animals, they use this balloon, this interface, to walk around. This small insect, you can see it can walk on the water. This is a picture that I like a lot. It has like this bee here, and under, so the sun is there, and the shadow, you see these big round things on the feet here. So this is the reflex of this kind of like a deformation of this balloon, the structure of the surface tension. And this is a big cat we have in Brazil, where I come from. It's the only cat that likes water. It's the jaguar. And this picture was taken just before it broke through the surface tension of water. So I like it a lot, and that's the whole point here. If you put a little bit of soap on one of the sides of the fork, it breaks through this surface tension, and then it ruptures like that. And that is something that you can try to do at home and show it to your kids. And something else that perhaps you should not show to the kids is this phenomenon here. It's called tears of wine. If you drink wine later, you can see, if you swirl the glass a little bit like that, you can see some tears going around, falling down from the sides. And this is also connected to the surface tension between the wine and the air. And I'm not going to explain how it's connected, but it is. So just very close to finish, this is another experiment that we have started. It's another porous medium. There is some liquid flowing around, and then we just put some dye. And the idea was to put dye in a fixed place and see how that dye is transported, how the water moves this dye around. But I got bored, so I was just like doing this, you know, like putting in and out, like a needle there with dye. And it made this very interesting thing there that doesn't work anymore, but you got it. And I just want to finish with one last experiment. That's not an experiment, it's just an observation. But first, I want to talk a little bit about this huge painting here that I actually didn't know up to like maybe 6 months ago. So this is the new Munch Museum in Oslo. Big, beautiful building. And I just want to show this for the scale. This is a huge painting. And it's called Forskerne, the researchers. And you see who the researchers are. It's a bunch of kids on the beach. And you see what they are doing. The little girl here, that one there, the other friends there. They are just looking at nature. I think it's a wonderful title. And so they are researchers. And sometimes that's all we need to do. Like all the experiments that I have shown, they were kind of prepared. Like this thing right there, it's printed in a specific way. We have like liquids that are a bit specific and so on. But sometimes we just need to look at things very carefully and you see something interesting. And that's what happened in this one here. This is something that we don't have an explanation for yet. It's literally just a bunch of sand in a liquid, a bit like ketchup. It's what we call a non-Newtonian liquid, but it's just a weird liquid like ketchup. And then we just let it evaporate. No tricks, no 3D printing, no fancy things, just evaporating and a camera taking pictures. And this is what happened. It behaved in the most strange way. It started to move, it went inside, it made like some tips like this. It starts to look like an octagon, and then it continues to evaporate and evaporate and evaporate, and it starts to get a bit darker there, and I really don't know what's going on. So this is something that is ongoing. We just started to do. Maybe we could get some ideas from the artists, because the scientists are a bit lost at this. We really don't know what's happening there. But yeah, it's something for the future. So with that, I want to thank you all once again, and most important, thanks to Mirella for this wonderful opportunity that I think has been really, really good for all of us. So thank you.